Hello, and welcome to everyone viewing this session on the joy of circuit design within the ISSCC 2022 Circuits Insight program. Now, my name is Naveen Verma, and I'm a professor in the Department of Electrical and Computer Engineering at Princeton University, where I'm also the director of the Keller Center, which focuses on innovation and entrepreneurship. I'm certain that within the Circuits Insight program, you're seeing that circuit design is a source of profound impact on individuals in the world and society as a whole. It's a source of delight and creative outlet for the designers themselves. And it's ultimately a source of infinite possibilities for solving the most challenging problems of the future. Now, in this session, you will see all of this come to life from the perspectives of giants in the field, pioneers who have shaped circuit design and its impacts on the world. You've probably heard of these individuals and may view them with some amount of awe, but you'll see that circuit design and the powerful ways they have wielded it has first and foremost been a source of personal joy and humility for them all. So without further delay, let's go ahead and get started with this session on the joy of circuit design. And to do that, let me start by introducing our panelists. Let me start by asking Professor Asad Abidi to give him a little self-introduction of himself.
Hello, my name is Asad Abidi. I am a professor of electrical engineering at the University of California, Los Angeles, UCLA. My research interests are in analog and RF IC design. What got me into circuit design was the inspiring lectures of an undergraduate teacher, Tom Odell, who enthused about the beauty of circuits, and he had learned the art of circuit design on his own and communicated it very effectively.
Thank you very much, Asad, and welcome. Next, Professor Anantha Chandrakasan, would you please introduce yourself?
Hi, everyone. I'm Anantha Chandrakasan, a faculty member in the Department of Electrical Engineering and Computer Science at MIT. I also serve as the Dean of Engineering. My research is in the broad area of energy-efficient integrated circuits and systems, particularly focused on low-power and self-powered IoT devices, biomedical systems, and hardware security. My interest in electronics generally got started in high school in India when I took a programming course. But it was really my incredible experience as an undergraduate researcher in the lab of Professor Robert Broderson at UC Berkeley that exposed me to the huge potential of what integrated circuits could do.
Thank you very much, Professor Chandrakasan, and welcome. Next, Professor Tom Lee, would you please introduce yourself?
Hi, I'm Tom Lee from Stanford University. I've been there for about 30 years now. I'm now teaching the children of my initial group of students, so that calibrates the timeline a little bit. I like any circuit thing that sort of exists between 0 and 1. So that's the part of the universe that I'm interested in. I became interested in electronics just as a hobbyist, and it was only much later that I found out that you could actually make a living at it. So, hey, that sounds like a pretty good deal.
Thank you very much, Professor Lee, and welcome to the panel. And now, Professor Jan Rabai, if you could please introduce yourself.
I am Jan Rabai. I'm a faculty member at the University of California, Berkeley, in the EECS department. And my area of circuits is basically everything. I call it mixed signal, but it goes from analog to digital to RF to energy harvesting, power circuits, whatever you name, I'll do it. And the main reason I do that, and I really got attracted to this area, is the cool things you can do with circuits, the enabling factor of circuits in so many different domains. And that's really still what keeps me going.
Thank you very much, and welcome to the panel. Professor Willie Sanson, would you please now do a self-intro?
Hello, my name is Willie Sanson. I spent most of my life at the University of Leuven in Belgium. And I've been all my life in analog design, only analog design. And how I got in there? I try to answer two questions. The first one is, how do I have to change the electronics to improve the sound of music? That was the first one. And the second one is very different. It says, when you put two electrodes on your arm or two electrodes in in a banana or a kiwi and you measure the impedance, the first thing you have to do, why is it always different? That's what I wanted to say.
Thank you very much. And those are very motivating questions. So welcome to the panel to you as well. Finally, Professor Casey Smith, would you please introduce yourself?
I'm Ken Smith, University of Toronto. I started here in 1965 after a period at the University of Illinois. I've been interested in general in low frequency electronics from an early age. Think about 7 or 8 or 8 or 9. I gradually I did that because my father was an auto mechanic who provided interesting electronic or electrical components that I could experiment with, and he encouraged this sort of thing. I've continued on broadening my interest to higher and higher frequencies, and the need rises, although I'm generally a low frequency person who does what it takes to as high a frequency as one can get. Thank you.
Thank you very much. Once again, welcome to all of the panelists. So this is the exciting time. Let's chat a little bit about some of your experiences and how those have really shaped yourselves, but also the field. And I'd like to start maybe with a question to Tom, Assad, and Casey, to you. And the question is, look, circuit design is so much more than KCL and KVL, which is what we learned in that first course. And it's so much more than device IV curves, and it's so much more than running simulations. So really, the essence of the question is, what is circuit design to you? And over the course of your career, what have you found to be notably empowering about circuit design? Maybe, Tom, let's start with you, if you're okay.
Oh, I love these small questions to be answered in 30 seconds. So for me, I guess circuit design gives me an outlet because I'm a frustrated artist. I can't draw to save my life. So putting circuits together, it turns out to be just fun. I mean, I love to solve crossword puzzles. So circuits are just another expression of that sort of thing. I love the fact that it's kind of like music. And I'm a violinist and again, a failed musician at that. So I enjoy circuits because it gives me a chance to express that side to me. And it turns out that some of the output is occasionally useful to other humans. So that's pretty fulfilling.
Very good. And what have you found really empowering about circuit design in your career?
Well, it really is the ability to leverage the base technology that all of our species has managed to put together over the last century or so of electronics, and to create things that hopefully elevate the human condition. That's, it sounds grandiose, but that's kind of what electrical engineers have delivered. They've delivered on the promise of magic, I think, fairly successfully and consistently.
Assad, how about you? What is circuit design to you, and what has been so empowering about it over the course of your career?
Well, there is, of course, the artistic side of putting elements together to accomplish functions, but it's much more than that. When one works in analog circuits, it's not just functionality. There are so many difficult and ultimately beautiful outcomes, such as linearity and bandwidth and responses at certain frequencies which seem difficult. All of these things are challenging because they're solving real life problems, but the act of designing circuits is one where you bring together a knowledge of circuits as you possess it with the creative part of assembling things together, sometimes in unusual ways, and a formalism that guides it all. This is not just a matter of pure artistic expression, but rather guided by a disciplined sense of how to configure things, following laws of physics, following laws of signal processing, and obviously the KCL and KVL. So it's so many things that come together in one place and ultimately accomplish what you set out to do. And I add the word beautifully so, in the sense that these circuits approach mathematical operations almost ideally, very, very closely. And that, I think, is very, very special to analog circuits.
Thank you very much. Casey, how about you? What is circuit design to you?
Well, it's an unusual opportunity to be as creative as one needs in some area. My history is one of finding peculiar aspects of available problems and available circuits that fit somehow. Opportunism in an active way. I started out as an experimental person. I didn't know much. I continued really this way. As I learned more and more, I just followed the branch or followed the hint or something and did more of the same.
Perfect. Now I've got a slightly different question, maybe to Anantha and Jan. Circuit design, as Tom and Assad and Casey have described it, is really this infinite canvas, which you have taken, you two in particular, in all sorts of directions, really with the sky being the limit. Now, looking forward, what do you find really exciting about circuit design? Maybe Anantha, let's start with you.
Sure. I mean, first of all, it's truly remarkable what the power of technology scaling has allowed us to do, right? To incorporate incredible amount of functionality in a tiny piece of silicon. I see sort of three broad directions. First is to leverage the power of semiconductors to realize innovative applications for health or for life sciences more broadly, or for developing the next generation of energy efficient artificial intelligence solutions by leveraging our growing understanding of how the human brain works. A second direction is basically to develop circuits for emerging technologies, whether it's carbon nanotubes or with quantum sensing or interfacing biology to circuits. And the third is to explore the role of circuits to address the most challenging problems of our times, such as climate change and sustainability. And here, the opportunities for impact have yet to be defined.
Yeah, that's perfect and I think appropriately wide-ranging. Jan, tell us a little bit from your perspective. What do you find exciting about circuit design and its future?
I think Anantha kind of touched some things already there. In fact, what we have been doing over the last 50 years is carrying more and more functionality in ever smaller devices and more devices, to the point now that electronics is everywhere and circuits are everywhere. In every piece of our life, we are running into electronics at every second we walk around and anywhere around. So, and this is going to continue. And as a result of that, we are indeed creating a different world. We're impacting humanity, we're impacting society. And this will not stop. I think the concept of the distributed intelligence, for instance, the capability of making smart devices interact with us as humans, making things better for our world, basically dealing again with climate change and all this type of fire, all those things matter a lot. So to me, it is the ubiquity of electronics, the ubiquity of artificial devices that create some form of intelligence is what is really exciting, but also scary.
Mm-hmm. Yeah, I think these are well said. These are reflections on kind of where circuit design can go. Let me ask a slightly different question to you, Willie, and maybe also to you, Tom. And the question is, circuit design has been just an incredibly dynamic field. What has remained the same? And in your view, what has changed the most as we've progressed in this area? Maybe, Willie, let's start with you.
it's a dynamic field, all right. To me, analog circuit design has learned to make decisions because there is an enormous number of variety now, 10 years ago, 20 years ago, 30 years ago. And because there is always an unlimited number of possibilities there, whether it is number of specs or number of ways to design a circuit, it's always unlimited. You can always add something. So that means that when you ask two designers to design the same thing, you will have something else because they take the decisions at a different point in time. And this is the dynamics of circuit design, taking decisions at a different time.
So there's dynamics within circuits, and then of course there's the dynamics of the field. Now, Tom, I know you've been a real student of the history and culture of circuit design. So I'm curious what your thoughts are on how this dynamic field has remained the same, but also, you know, what for you has changed the most about it?
Well, the fundamentals certainly have stayed constant. That's sort of a tautological statement, but certainly, you know, KVL isn't going to disappear anytime soon. But what's changed is the incredible effect of Moore's law. I mean, an exponential scaling downward lithography-wise has enabled and also forced us to think in terms of systems. So it's no longer all about, well, gee, I can interconnect these two resistors in some new way and develop a new capability. A certain amount of that continues, but the big impactful research is on how to build larger systems. And so we're just now starting to grapple with that problem. I mean, how do you design something that contains 30 billion transistors with a finite number of engineers? I mean, the number of engineers has not grown exponentially, and yet we're called upon in linear time to produce exponentially more complex systems. So that's probably going to be the big theme of the rest of the century, is how to grapple with scales that are so large that even moderately large teams of engineers can't stand the entire elephant.
That's very interesting. I think that you know, we need to grapple with that complexity to be sure, just when you look at some of the real grand challenges that we face. So I'd love to come back to a point that I think, Anantha, you and Jan, you raised, which is circuit design and its intersection with some of the grand challenges of today. So circuit design, integrated circuits have arguably been the most critical skill and technology really affecting society in the past 60 years. How do you see circuit design intersecting with some of these grand challenges of today and tomorrow? Climate change, broad human health, social justice, economic justice, those sorts of things. I think, Anantha, you started to speak a little bit to this. Please share more.
Yeah, I mean, I definitely see addressing climate change as one of the biggest opportunities for circuit designers. I mean, there's obvious things that we could do, such as building more energy efficient circuits for cloud computing, such as using accelerators, or the role of power electronics in electrification, right? So there's already many things that we're doing that's directly impacting climate change. But there are many more opportunities that are yet to be defined. Just like we think about materials and the choice of materials at the end of use, we should be thinking more formally about hardware at the end of use. So there's a lot of opportunities, I think, when we think about circuit design and climate change, and yet those opportunities are yet to be defined.
Yeah, thanks, Anantha. So maybe, Jan, your thoughts. What are your sort of favorite grand challenges that you think circuit design is just really teed up to solve?
I'm really interested in the healthcare wellness side of things, and I think it really requires that circuit designers have to keep an open mind, right? Basically interacting with people in the field and hearing what are interesting things that might emerge and what can be done. And very often, when you have that conversation, the first thing you hear is you say, "Well, that's not really interesting, it's too simple." And you say, "Challenge us." And when they challenge you, they come up with something. They say, "Well, that's impossible. We cannot do that." And then you start thinking, and you enable something which is truly amazing. And I think we will see how, for instance, the interaction of electronics with, for instance, biological cells will lead to some amazing things going forward. And I think we're on a pathway there, but there's a long way to go. And it requires inspiration, interaction, collaboration.
So I think those are all excellent points that really it behooves circuit designers to engage in those kinds of collaborations. Maybe we'll come back to that in a moment. Asad, did you want to speak to this as well a little bit?
Yes, you had mentioned social justice. So let me touch on that.
Sure.
The smartphone, of course, is the ultimate confluence of trends in circuit design in the last century. They all came together in a smartphone, made the most extraordinary device up to that time that is put into everyone's hands. The fact that there's a high-resolution imager built into a smartphone and that smartphones are in the hands of everybody has done more for social justice than I think anything else. All the unrest that we have seen has really been driven to some reasonable sort of outcomes, or at least along reasonable paths, because things are recorded in real time. Social injustice is being recorded and broadcast to the entire world to witness. I think ultimately that circuits used in this way will make the world a more just place for everyone.
Yeah, that's an excellent perspective. And when you think about the range of technologies, from those sensors to the computing technologies to the networking infrastructure, it really expresses some of the points that I think Jan and Ananta brought up about collaborations and sort of convergences that really become critical for the full potential of circuit design. Let's do the following. Let's move for some of these broad discussions around grand challenges and so on to some maybe more personal questions to each of you. And so maybe I'd like to ask Tom and Casey and Willie, I'd like to ask you the following. So moving from some of these broad impacts, a little bit back to your personal appeals, tell us about particularly memorable circuit designs that you've worked on, maybe because it was challenging, maybe because it was delighting, maybe because it was particularly impactful. But take us back to an experience like that you might have had, Tom.
Well, things that I had direct experience with, probably, working on PLLs. PLLs continue to fascinate me. They have weird pathological modes, which themselves are interesting. And of course, if you're working for someone else, they don't want you to marvel at the interesting nature of the problem. They want you to solve it. But certainly working on PLLs for a bunch of different contexts, whether it's wireless telecom or for fast serial links, PLLs were just a great way to express analog, fun in an impactful way. But in terms of circuits that I've studied that I think, probably had much greater impact, just looking at what the world of instrumentation engineering has produced, because they have a very difficult problem. If you think about it this way, they live in the same universe that we inhabit. They've got the same technology to draw from, and yet we trust them to build a box that tells us what our box does. Mm-hmm. So they just have to be smarter than us. Mm-hmm. And so studying their circuits, which are to a large degree not documented in easily accessible literature, that's been a fantastic bit of education. And I've been trying to sort of spread some of this stuff to the extent that attorneys permit. But that is something that I would recommend students who are interested in circuit design just start rummaging through old HP and Tektronix manuals, and you'll find just nuggets of gold waiting to be picked up by someone who's interested.
Very interesting. Maybe, Willie, the same question to you. Tell us about a particularly memorable circuit design experience that you may have had.
Well, the circuitry I'm thinking about right now, that was a very rewarding experience, was the first generations of cochlear implants, where we started in 70s, 75 to 80, 82, 83, the first 3-5 generation, then taking up, because in a cochlear implant, you have to do some impedance measurement, and that involves electrodes. You have to do programmable stimulators. You have to have a microprocessor in there to do all things, and all on nothing in terms of power. And the nice thing about it is that 30, 40 years later, people come to you and they say, gee, how great that the cochlear implant got developed. And they are so thankful. Well, there are very few circuits that I can see in my background that people got enthusiastic about. The cochlear implant is one for sure.
Thank you very much. Professor Smith, Casey, tell us a little bit about a circuit that you might have worked on that's particularly memorable or has some personal appeal for you.
Okay. Well, such a circuit probably exists in the early stages of computing that I was involved with, and I was entered computing at the vacuum tube transistor age, and the initial designs were very big and bulky sorts of things. And then as time proceeded, not very far into the transistor age in the early 60s and so on, transistors became more reducible or size-wise, and the net result was much more complexity in a smaller space, and it was concerned for power and all that kind of thing. And one found compromises that were reasonable and appropriate and quite successful in their context. So that looking back at that far is difficult to analogize to the modern era, where of course things are so small that the techniques that I'm steeped in or buried in historically are crude by standards of things that you cannot see, or takes much age to help you see.
Yeah, thanks a lot for this. I hear, Casey and Willie and Tom in all of your descriptions, just sort of a richness in the things you've had to work on and the skills you've had to bring together. So maybe a question, Willie, Assad, and Jan, for you, is that circuit design is really an integration of many different skills and the ability to bring together and leverage those skills creatively. Now, what are some of the skills and maybe attributes that you found to be particularly important that have been ones that you've really leveraged as a circuit designer or a researcher over the years? Maybe Willie, let's start with you. What are some of these skills that you found are really critical to bring together, or even attributes as a designer or researcher?
Well, of course, there is a minimum of mathematics that you need to know before you can handle circuitry. But then, of course, you don't need the stepping stone towards a simulator. What you have to do is to solve equations. And the most important aspect of solving equations is to which level are you going to simplify the equations? Because if you simplify too much, you figure out G, 0 equals 0. That's too much. But if you don't simplify enough, then you figure out on the fourth space of your equations, there is an error. You have to do all over again. So simplifying equations to me is a major achievement of a successful circuit designer.
Yeah, and perhaps that speaks to intuition and an understanding of when you can simplify and how you can use some of these complex equations in which ways. Maybe
intuition is not existing. Intuition is something you create by doing it. It's something that you grow. Nobody has an intuition, but you can grow intuition. And that's why analog design is lifelong learning. The only thing you do is create intuition.
Very good. Now, I suspect, Assad, that this is an area that you'll be able to pick up on immediately. Tell us a little bit, in your views, what are some of the really critical skills and attributes to fully excel and be able to unleash your potential as a circuit designer?
Well, I think what Willie said is, of course, the first and perhaps most important step, but I'd like to go beyond that. Learning how currents flow in loops and how voltages distribute themselves across linear and nonlinear things is a very important part of developing that intuition. If one doesn't do that, one really cannot design circuits of any complexity, and one can certainly not troubleshoot problems. In terms of learning how to deal with equations, yes, they will never leave us. But what I'd like to add to what Willie said was that that in analog circuits, there are lots of equations that cannot be solved. They're nonlinear because our working devices are inherently nonlinear. In fact, they wouldn't amplify if they were not. So dealing with nonlinearity without getting stumped over it because you don't have graphical intuition and other intuition is a very, very important part of doing circuits. Learning how to treat things qualitatively, graphically, which leads to good enough solution and guides your exploration is very important. I think also one has to, in these days, be very wary of the opiate of simulators. Our simulators are extremely good, and the machines on which they run are very fast, and they get better and better. And it's very easy to lose courage and rely on simulators to replace the hard thinking that goes behind all of this. I would advise newcomers to the area to be very cautious about falling into that trap, because if one does, one's ability to create and enjoy the outcomes is seriously curtailed. Unfortunately, the majority of the industry runs on precisely this style of circuit design. So, but I'm not sure if that necessarily brings the joy that we are talking about in this panel discussion.
Okay, very interesting. Now, these are two perspectives that have talked a little bit about how to really harness circuits themselves, but there's also all of these areas around circuits that you can harness within the canvas of circuit design. So maybe Jan, love your perspectives on what are some of the skills and attributes really that circuit design helps us synthesize together that in your view have been really powerful or have brought a lot of leverage.
Actually, I'm going to start building a little bit on what both Willie and Assad said, but going from a digital perspective, we've talked primarily about analog circuits. Even now, think about digital. It's amazing, right? We're designing circuits with billions of devices, the imperfect devices, and make this thing work consistently. That's incredible. And there's a set of skills that come with it. There's a set of insights that come with it. And you may call it mathematics or equation, but we call it abstractions, right? The capability of abstracting away some function and forget about some of the details that might not matter at that point in time. And do this rightly, because obviously we can start thinking at some point in time a transistor becomes a switch, and a switch becomes a gate, and a gate becomes an instruction, and so on and so forth. Those type of things are extremely very helpful, but at the same time, if you ignore too much, you end up with something that's unmanageable, right? Basically, you forget about the physics that ultimately drive things. You forget about energy. You basically forget about performance and things like that. So the art of trying to figure out what is important, what do I have to carry over to the next layer, is really important. And again, this is not something that comes easily. You may call it intuition. I call it almost improvisation. And just to give you a thought here, I once asked a musician, a performing musician, about how come they can improvise. Well, how do you do that? Suddenly you start playing a tune that out of the blue, and then you end up with something that is basically where you started off. That's amazing. And his answer was very simple. He said, you practice a lot. That's the way you start understanding the field or what you do as much as possible. And then you have the capability of expanding out and doing new things and exciting things around it.
Very, very interesting insight. I want to sort of take from this question about what sorts of skills are useful to the circuit designer and maybe broaden how the circuit designer is useful to the rest of the world. So Ananta, maybe a question to you, and maybe Jan, I'll come back to you because you started the ball rolling in this direction. The power of circuit design has made it an enabler of so many new capabilities in so many different fields. Tell us about some of your collaborations with designers and researchers outside of this field, and how circuit design has enabled new capabilities in those fields?
Sure. I mean, there's, first of all, I'll say this is the aspect of being a researcher that I enjoy the most, which is collaborating with others and learning new ideas and new areas. And I've had so many collaborations. But one that I will pick up on is our collaboration with Dr. Tina Stankiewicz, which involved basically harvesting energy from the inner ear, which contains a biological battery. So it's an endocochlear potential. It's truly an interdisciplinary project, and our teams work together to demonstrate energy harvesting from a pig. So in fact, we were able to harvest just a tiny bit of energy, right? Nanoamps of current, but we were able to buffer it and then power a wireless device. So very exciting. And it was really interesting to hear Willie talk about the cochlear implant, because we also worked with Tina to realize a fully implantable cochlear implant that has no external device. And this is probably the project that has got most interest from the public. I completely agree with Willie. This is, this really means that you should think about projects that can have impact, right, ultimately. So that at the end of the day, how is this going to help society at large? So to me, that was a very satisfying collaboration.
Okay, thank you, Nathan. Now, Jan, you also started to pick up on this, and you made mention of it before. Circuit design has had such incredible impact across so many different fields. How about some of the collaborations that you've been involved with? What are some of the memorable ones? How has circuit design really enabled new things in new places?
Yeah, so now actually, this is kind of the driver for me. Is basically those interactions is what inspires a lot of what I do and my students do. And I can give examples from a number of fields, basically building on what Ananta already said. The field of neuroscience is quite incredible, both from a medical perspective as well as a computational neuroscience perspective. So it is amazing when you start building your little circuit and you see it actually ending up in a primate, and you start seeing signals coming from the brain that are wirelessly transmitted, and you can do this for a long period of time. That's really rewarding. And basically talking to those people, basically being basically neurosurgeons that every day basically implant devices for Parkinson patients and things like that, hear what they would like to see and think about what you can help them with is a very important step forward. But I've worked with other people. I've been very excited about, I like wine a lot, working with people in the agricultural field, basically figure out how to monitor growth of vines, but also looking at the process of the fermentation, how wine develops over time. Having electronics to help that process is really cool. So many different domains, but you have to have you keep your mind open. You basically talk to people, say, what are the opportunities that I see here, and what can we do for you? And how can we work together? That's kind of the key thing you need to think about and basically explore.
Yeah, and I think the way that you described it, Jan, is that that's really been a source of inspiration for you. And I think that it's a source of inspiration that pushes you to learn in areas that are not just circuit design, but that are around circuit design and that connect to circuit design. And so I'd love to get your perspectives, Tom, and maybe KC and also Assad, where sort of being a canvas where you've been able to express, unleash, bring together creativity from so many different areas. What are some of these areas, maybe outside of circuits, that you found to be really useful in enabling your creativity as a circuit designer? What are important skills or areas of knowledge to focus on that are adjacent to circuit design to sort of broaden one's capabilities, perspectives, and impact? Tom, maybe let's start with you on that one.
Okay, I love these small scope questions that you ask. So
so far you're doing really well with them.
Well, as we develop the ability to go to higher levels of complexity, as Jan said, we have to look at how to attack the problem at the right level of the hierarchy. But in that simplification that sort of implicitly comes along with that exercise, you have to acknowledge what you've left behind and make sure that you've actually done this pruning thoughtfully. And at the same time, you find that the scaling that you've enabled inevitably brings you into contact with adjacent fields and maybe not even adjacent fields. And people have here today talked about neuroscience as being one of those areas. And, I'm certainly one of those who has started to look broadly at that problem or the set of problems that they've been studying. And I've been very lucky that Stanford has a med school co-located on the campus. And in fact, it's within walking distance of my office. And again, by another bit of good luck, one of the colleagues there who's interested in sort of the things that I'm sort of starting to get interested in actually started off as an electrical engineer and then sort of mutated into a neuroscientist, but always with the perspective of an electrical engineer. So we started to identify a very interesting set of problems ranging from just information theoretical approaches to understanding what the brain does as an information processing machine, and then seeing if we can map any of those insights into therapeutics, which is what she's focused on, and low energy computational fabrics. But still leaving the world of 0 and 1 behind to try to obtain some of the benefits that nature has already managed to deliver over 1 billion years of evolution, to see what interesting things we can do on, 25 watts for the human brain is pretty spectacular. And especially more spectacular when you consider it consists of transistors, quote unquote, that switch in millisecond speeds. So to a certain extent, you might say, we've got a big problem here with the end of Moore's law, but nature has already given us an existence proof that's possible to do really remarkable things with kind of crappy transistors on a very, very tiny power budget. So I think unlocking the secret of how nature pulled that trick off is going to enable us to propel the rest of the century forward technologically.
Yeah, sort of nature-inspired or biologically inspired circuits and architecture is certainly an area that we can leverage a lot, circuit designers, through our very powerful technology fabric. Casey, maybe tell us a little bit from your perspectives, what are skills or areas of knowledge that you think around circuit design have been very powerful for you?
Well, it's very, very interesting to step back and wonder what actually influenced one. Any success I've had is all about trying to discover, realize some peculiar property of somebody else's field that interacted with my own, that I could use electrical things to explain or to motivate or to encourage further development of. And that sort of history of being willing to listen to diverse, unusual experiences and trying to understand them in terms of more conventional to us, or to me in particular, electrical way of looking at it. So that arrangement or that pattern has been very important.
So that's fascinating. The idea that circuits can be a model for how so much else in the world operates, and to help us understand that.
That you precisely.
Thanks for that, Casey. Maybe Assad, how about you? What are areas around circuit design that you think are very powerful for circuit designers to know about?
Well, I'm going to talk about something that's markedly retrograde compared to all these neuro inspirations and so on. And I would say that I have been most profoundly influenced by and learned from the area of communication systems and how that can influence the design of circuits. Communication systems is something that is developed on a very abstract view of what circuits can do, but it's got a life of its own. And when one studies the ways in which communications, whether they're short-term or short range or long range, employ methods, there's a lot to be inspired by there in designing circuits for entirely different solutions. Most recently, I was studying exactly how a GPS does location finding to ultimately to millimeter accuracy. And the way that is done is truly, truly amazing. And one learns things there that one could apply to circuit design in other application areas. So in my own case, communications and signal processing have been very profound influences.
Yeah, certainly being able to actually respect and take into consideration physical effects like noise and other systems like communication systems that allow us to do that in the world of circuits makes our bag of tricks and capabilities even more powerful. So thanks very much for those perspectives. Let me ask the following question, and maybe we'll go, Jan, to you, and also Willie, to you with this one. You know, look, if you're a young circuit designer, it seems like there's so many different kinds and applications of circuit design. There's analog, there's digital, there's RF, there's amplifiers, data or power converters, computing circuits and architectures. There's so much. How should students decide how and where to approach the field? How should they think about that? Jan, maybe let's start with you. As somebody who's worked on everything.
Right. So I kind of take a top-down perspective on this. You start from what inspires you, what basically makes you excited. Basically might be application, might be something that is in the medical or biological space, or might something that basically environmental. And then you work from there. What are the set of skills I would like to need to have to basically enable some of those things? And it might be starting with a little radio or something like that allows you to communication, or it might be that you need some front-end processor that translates the signals into something analog. But yeah, I'm basically, I'm more like starting from the goal out, and then basically from there on, try to figure out what skills should I build up over time, rather than saying I'm going to build a lot of those. I'm going to start with analog because I think that's a cool thing. But again, that might change different from person to person. But that's the way, at least I think, it basically start from where you would like to go, and then work it out from there.
Very good. How about you, Willie? What are the ways to navigate this, sort of jungle of all of these different kinds and applications of circuits?
Well, you learn about that when you try to figure out why students choose a particular project, a particular thesis or something, and you ask them, why do you choose this and why do you choose that? And then you hear that they would like to see an important problem solved that I understand. For example, a medical problem that, of course, you have to tune it down to something technical because you're not going to save the world in the thesis. But at least you have to show in some of those theses how the world could be affected after so many years and so many circuit designs. You have to show them that, otherwise they are not interested. So somehow to interest people, you have to talk about major problems, whether it is climate change, they all jump on that. Whether it is shortage of energy, they jump on that. Whether it is a biomedical problem, how chemical sensors, for example, all those chemical sensors which don't exist. How about the circuitry to turn lousy sensors into good sensors? So you have to really show the perspective of all the technical circuits and show in the long end where it leads to. And I think that's very important. We have missed out on that too often, but after the end, we have learned to do that.
Very good. Let me ask another question, and maybe this one's for you, Tom. There's still so much we don't know about circuit design and so much untapped potential for what can be done. And I think that this requires, fundamental research. It requires applied research, but also product development so that we can bring those capabilities to society where they're needed. How should students think about this relationship between academic research, industrial research, and product development? How can you bring those together in all the ways that we might aspire to?
Wow. Okay. Well, so the beauty of Moore's law is that it has enabled us to build things of grand scale. The challenge that comes along with that is, how do you actually grasp such a complex beast? And one of the problems that I see actually with the way that we teach students is there's a little bit of a disconnect between what we reward students for in university settings and what they're rewarded for in industry. You know, we reward creativity and innovation, and then they go to companies and they find out that that's actually not what the rewards are set up for, because it's very disruptive to say, well, you know, I got a better way to do an amplifier. And you say, well, we already have an amplifier that works. Well, yeah, but mine's better. So why don't we do that? And it's a really tough adjustment that many students undergo when they find out they're actually not incentivized to create. You just have to get to the next node quickly, and don't risk missing the next node, because then our competitors will kill us. So that's been a problem actually for quite a while. Now, I'm actually an optimist, and looking at the end of photolithographic scaling gives us an opportunity now to reward innovation, truly reward innovation. Again, for the first time in maybe a half century, because we're not going to be able to rely on the next node to deliver us from the current situation. We're actually going to have to come up with some true new things. And I'm excited about that. And so I tell my students, I don't know what the future holds exactly. No one does. Anyone who claims to know is lying or deluding somebody, themselves and you. And so the best thing that you can do to guard against obsolescence and to play well in whatever the future unfolds is just to have a good grounding in the fundamentals, because those are always going to be valuable. And you can pivot very quickly and acquire what additional, you know, auxiliary skills you need to finish off the ability to do something. And so as the future evolves, you'll be in a good position because you'll be agile, you'll have the tools. And the other people will say, oh, but I only know how to get to the next node. Well, you know, they will not have as fulfilling a career in this century. So that's my best advice, is just sort of this meta advice, is just stay smart and get to know a lot of smart people.
So I think the point that you're making is there's a need now more than ever for, you know, sort of fundamental applied research and product development to be tightly coupled together. And we all need to sort of understand where we can leverage from those different domains.
Absolutely.
Well, look, guys, we're almost at the end of this session. And so I want to ask a last and very important question to each of you. And once again, I hope that you'll be able to answer this very deep question in 30 seconds, but you've done so well so far. I hope you will be. And so the question is the following. A lot of the students who are watching this are new and they're aspiring circuit designers, and they will and would like to have the kind of impact that you have had. So the question is, what would your advice be to these new and inspiring circuit designers who in many cases are starting their careers? Let me start, Willie, with you.
Start their career. That's a tough one. Then of course you have to leave the level of circuit design. You have to go higher than that. You have to understand what circuit design can mean on a higher level, on a system level, which has been said before. The other thing that you have to know for the rest of your life, you have to know something about noise and something about distortion, and then you are in good shape.
Very good. Jan, let's hear it from you. What would your advice be for new and aspiring circuit designers?
Okay. My thinking is that, well, the most important thing is to think big. Never be afraid of something that's hard or that deems to be impossible. Go for it. I think that's what creates the excitement, that's create innovation. So again, think big. Very
good. Casey, your advice, please.
Yeah, I think thinking big and beyond the conventional boxes. Just what happens if something strange occurs, some unlikely event? Is there a consequence that might be useful?
Very good. Looking for the unexpected. Ananta, let's hear it from you. What is your advice to new and aspiring circuit designers?
Yeah, first of all, I think it's a really exciting time to enter the circuit design field. As Tom mentioned earlier, the opportunities to create systems or do circuit design with a system focus is really enormous. And my advice would be to pick problem areas that you're most excited about and to explore bold and non-incremental approaches to make an impact, very similar to what Jan and others have also said. I would also recommend a broader education. Many of the exciting solutions come from multidisciplinary approaches. For example, for circuit designers, I think machine learning is a very important tool. And it's used now to solve so many problems, from material synthesis to drug discovery to understanding biological mechanisms. So that's an example of something that could create broader impact.
Very good. Tom, what have you got for us? Advice for new and aspiring circuit designers.
Pick a hard problem that forces you to build up some muscles so that you can become your own best teacher, because the information that we convey at the university level starts to rot about the time that we hand you the diploma. So if you're going to have a long-lived, fruitful career, you're just going to have to be your own best teacher and stay current. And that requires you to have some joy in the activity, because otherwise it's just drudgery, and who needs to live a life like that? So find some hard problem that also brings you joy and just keep doing that, and you'll probably have a good life.
Perfect. Assad, let's hear it from you.
Advice. I'm going to echo Bertrand Russell, who said, if you want to be successful in life, choose your parents well. For the new circuit designer, that the advice translates, choose your teachers well. All of the wise advice that we've just learned is only possible if you get off on a flying start, which requires that you have a good teacher to begin with. You can only teach yourself well if someone taught you well to bring you to that place. And so choose your teachers well, learn many things and deep insights from them that are not easily found, and then deploy them for the rest of your life on your own.
Very good. These are perfect pieces of advice. And with that, I'm going to close the session. I hope what people got out of this session, I think what I got out of it is, of course, circuit design has had, will have enormous impact in ways that we can't even imagine. And the proof is right here in this session and the experiences of the people from this session. But what we also saw from the experiences of the folks in this session is that this is a very personal thing. And the delights and joys of circuit design and the ability to have that impact is one that must be and is aligned with all of the things that really make us happy inside, our ability to unleash creativity through these fascinating devices and fundamentals that become this canvas for our creativity. And so with that, I'm going to thank all of our panelists once again. I'm going to thank everyone for viewing this session, and we'll go ahead and close the session at this point. Thank you very much to everyone.